Hello, welcome all. Welcome to the fourth video on Code First Machine Learning. In this video, we are going to take a look at some of the mathematical libraries we have and starting with statistics. So here's the structure of the application that we have already taken a look in the first three videos where we looked at the design. So as we have seen, there's a code base, there's a unit test, and under code base, we have the algorithms, common, and math. Now we have created a separate folder for math because mathematical functions and routines are very important. In fact, they serve as the foundation for everything else we are doing. And if you're familiar with machine learning, modern machine learning is nothing but statistics. It's a more sophisticated form of statistics with applying some logic that computer science provides. So it's a blend of mathematics and computer science. And most of the functionality that we do are leverage some of the statistical functions. So whether you are doing like correlation or trying to find which feature set has an impact on your final value, all of that requires statistics functions. And then we also have a separate library for matrix computations that we are going to look in the next video. Matrix computations are also required for solving equations, finding correlations, and a lot of other things. So before you start work on any machine learning library, you need to have these base mathematical functions in place. So in this video, we are going to take a look at the statistics library. So expanding the statistics library, we see that we have five main classes: dispersion, dispersion beta, distribution normal, information game, and logarithm. Now if we expand the unit tests, go to the unit test library on math, we have the statistics, and as you can see, we have specific functions for logarithm, information gain, and each one of these classes that we have given. Now we have only one function for distribution, so we haven't split the distribution beta and normal in the unit test. So let's go back into the code base. Let's take a look at the dispersion functions. So if you look at the functions that are provided, so we have the mean, median, mode, the standard deviation for population, then standard deviation for sample, and then variance, and also the variance sample and the covariance function, as well as finding the correlation of Pearson. So looking at the, for example, the mean, pretty straightforward. You take a single dimension array, compute the value, and what we are doing, we are leveraging some of the functions that are already available in C sharp. So C sharp has a function that can give us the average of all the values. Now we are also leveraging the mathematical library in C sharp, and that is very useful to compute the power and some common mathematical functions. Now I'm not going to show you where each of these mathematical routines have been taken, but these are commonly well known. For example, when you're taking the variance of a population, this is the formula for variance, where you take the sum and compute the count and subtract the mean square. Similarly, variance population also has a slightly different formula. In the variance population, we pass the mean as a function parameter. Now here's a more detailed computation where we have taken the variance of the sample. So these are again standard mathematical routines, and you can reference any other mathematical source like Wikipedia article or other mathematical books to get an idea how we compute the variance sample. Now what we have done here is try to parallelize as much as possible wherever it's possible, right? In some case, if you have to lock or put too many locks in place, then parallelization doesn't make sense. Now for parallelization, we are using the parallel or the task parallel library that is available in C sharp, and most of the computations can be computed in parallel if there's a routine. For example, here we have to add, so we put a lock there, and lock is a construct that is available in C sharp to lock a critical section, or if there's something you only want one thread at a time to execute. So the task parallel library in C sharp is really very good. That helps us to minimize the code, and it allows us to define a function like this, which is essentially like a lambda, where this for each You take the values, and for each value you compute and execute this function in parallel. It's a pretty compact way how we can execute parallelization. Similarly, we have the standard deviation of the population mean, sum, and the mode, and going on the medium and the range. Then we find the Pearson's correlation. Now again, Pearson's correlation is very important in machine learning when we have to find a correlation between different data sets. So in this case, we are taking a single dimensional array and returning the Pearson's correlation. Now, what we have done is referenced some common sources. So here I'm just open up a Wikipedia page for the Pearson's correlation, and if you take a look at the formula, this is what has been applied in code. Now, one thing important here is we have once we implement the code, we also have to write the unit test for it. So for example, here we are when we are looking at all these functions that we are testing. So here are independent functions to test each one of the mathematical routines. So let's take a look where we are testing the Pearson's correlation. So I'm just going to search for Pearson here. So we are finding the correlation and using the Pearson correlation here. So we are passing the two values. These are standard two single dimensional arrays, and if you go and say go to definition, they have been declared as private variables of the class. So here in the setData function, we assign these values. So here you're seeing TA has been assigned an array here, and these are fixed values, right? So you can do a computation by hand for the Pearson's computation and see what the value is, and then validate that the function or that is being called by the unit test is giving the same results. Now, in some cases, we have also used Python and R language to validate our code. So the same function can be executed in R or Python, and then you can compare the results on the unit test side and see if it's same. So we are using the assert on the unit test side to make sure that whatever the value that is computed is the same. So for example, here this is the sum function on the dispersion class, and if you have the value, we know will be computed to 89 because we have manually defined TA, so we are just comparing it. Now this helps us that anytime we make any changes in the sum function, we run a unit test, and if there's a breakage, we can immediately find that some functionality has been broken. Now another thing to realize here that dispersion has been added as a static class. So this way you don't need to instantiate this class, and a lot of the functions are available just by referencing the class name. And we can validate by the keyword static here. Now similarly, we have other classes like information game, which is basically dealing with entropy. Now we have implemented the Shannon's entropy function. Again, if you go on the Wikipedia page for Shannon's entropy, this is the formula that has been implemented. Now it's a little painstaking to implement these algorithms from scratch, so it's always better to break it up into steps and then compare the results at each step. So for here we have taken information game and comparing the Shannon's entropy. Now this wasn't the unit test. Let's go into the implementation. This is where the core function is, where Shannon's entropy is computed. Now as we have seen, there's no parallelization here because some routines are not suited for parallelization, and in this case entropy is one such routine. Now as we go ahead and continue working with this, and we find a new way where Shannon's entropy can be computed in a parallel way, we can always come back and replace this routine. The unit test is going to remain the same so that we can verify the results are accurate. Now in this case, on the assertion of Shannon's entropy, we have not like using an R equal. This is because this is a double value, and double values in any programming language are 64-bit values, and they are never accurate. Like there's always a floating point computation, what is called a tolerance that comes in. So we verify a double value by comparing it within a range. So here we are saying values greater than 2.17 or less than 2.19. So whenever you are comparing double values, never give an exact range on your unit test. But this is a good enough range, and anytime we make a change in the entropy function for Shannon, this is going to change. If this changes, we are going to get an error. That's what I meant there. Same for mean function, because the value is a double, then we are comparing it with a range. Going into the logarithm class, right now we only have a single function just to get log2, which is pretty straightforward. We may not need a function log2 because most of the common libraries in languages have a log2 function, but just for the sake of clarity and allowing us the capability to add further functions or any specialized functions that we may need anytime in the future for some new algorithms that we implement, we can always have that design pattern available to add it easily. Similarly, we have added a distribution beta class, but there's nothing on it right now because we only have the distribution normal. So having empty classes in place helps for our design pattern so that anytime we need it, then we can go ahead and easily add those. All right, with this said, I'd like to stop here and see you in the next video where we'll continue looking at the other mathematical libraries. Till then, see ya.